Hi folks, taking an experimental tour here, see if I can talk you through the Desmos activity, kind of a review of functions matching that we looked at in class today. So, here we go. Alright, we're starting at the very beginning. Calculus is the mathematics of change. I will skip getting to know you time. And let's match some graph with the slopes that best describes it. Okay, so first glance, I'm looking at these various lines and these various slopes floating around. The first thing that comes to mind for me is I want to sort between positive slopes and negative slopes, right? Thinking geometrically, a positive slope means our function is increasing, right? Our negative slope means it's decreasing as we sort of read across from left to right on the graph. And then of course we have this little slope of 0 in between. A slope of 0, rise over run, 0. Change in output versus change in input, 0. No change. I'm going to say that's the one and only horizontal line on this picture, right? Horizontal line, no change, slope of 0. Steady. Okay, now let's think about our examples of increasing functions. So lines with positive slopes. That looks like our 2. One of these is very steep, one of these is not so steep. Steepness would be a faster rate of change or a greater change in output for a single change in input. So I'm going to say that's a slope of 5. And this one down here is probably that slope of 1/2, right? That's sort of for every 2 units our input changes, the output changes by 1 unit. It's a more gentle slope. Okay, let's see if we can arrange the next ones in the same way. So here's a steep decrease, a less steep decrease, and the least steep decrease, right? So the most negative slope will correspond to that most steep decrease, right? We're saying for every 1 unit change in input, the output goes down by 3. Okay, next in line looks like a slope of 1, and then our most shallow example is a slope of 1/3, right? Change in output versus change in input, rise over run. However you like to think about slope, we're just sort of translating these quantities and relationships into this geometric context. Okay, let's keep going. I'm not going to tell you about my level of confidence. It's not as high as it should be, but okay, now things are getting extra interesting. We are what are we considering? We've got an exponential function, we've got a log function, we've got sines and cosines and tangents, and then we've got the real outliers, the secant and the arctan. Whoa there. Okay, let's start with these exponentials here. E to the x represents exponential growth with that natural base, e. The natural log is an inverse to that function. So which of these looks like exponential growth? I think it's this one. That right there looks like exponential growth. Now, the natural log function is the inverse of that. So we can imagine a diagonal line through the origin and say, okay, which one of these looks like a flip over that diagonal? Which one of these graphs looks like we swapped the x-axis with the y-axis and the y-axis with the x-axis, right? It's that one right there. Be matched, be friends. There we go. All right, so there's our natural log function versus our exponential function. Now let's get into the slightly more friendly trig functions, sine and cosine. Gut reaction says, oh yeah, those are periodic wavy lines, so I'm looking at these 2 down here. The big question is which one of these? So if I look at this graph, I notice, I'm going through the origin, and over here our y-intercept is up at 1, right? That's our big difference. So let's ask ourselves, what is the sine of 0 and what is the cosine of 0? Picturing our unit circle, the sine of 0 is 0. All right, I'm going to label that one as sine, and the cosine of 0 is 1, and so I'll label that graph as the cosine. There are many other ways to think about all of these, by the way. This is not like the one and only thought process. I'm just going with my gut and talking you through it. Okay, now things get interesting. Let's try to find ourselves a tangent. So tangent as a function, one way to think about tangent is sine over cosine. So if I'm looking for a graph of tangent, I'm looking for these outputs divided by these outputs. Let's see what we learn. Looking at the origin, sine divided by cosine looks like 0 divided by 1. Okay, so we're looking for a graph that goes through the origin. Here, don't got it. Here, got it. Here, also got it. Interesting. Okay, let's think about what happens later on. What happens with tangent if the sine is 1 and cosine is 0? Sine 1, cosine 0. For instance, at the angle pi over 2, right? Sine is 1, cosine is 0. 1 divided by 0. Oh no. Oh, that's a bad time, right? Let's not try to evaluate that exactly. Let's think about 1 divided by something getting smaller and smaller and smaller and smaller. That's outputs getting bigger and bigger and bigger and bigger, right? We have places where the tangent is undefined if the cosine is 0. So I'm looking for something where the function seems to shoot up off the graph, and there are these sort of asymptotes saying, well, it's not actually defined there, but close to there, it's huge. It's unreasonably huge. That looks like this, friend, huh? Very good. Now, choosing between secant and arctan. Let's think about arctan, right? Same thought process that we used with e to the x and the natural log of x. Those functions are in a pair of inverse functions. Tan and arctan, by definition, that's an inverse function relationship. So we're looking for that same sort of picture a diagonal line and flip this graph. That tells me I'm looking for those fun tan squiggles just turned sideways. And of course, I'm speeding past questions about sort of domain and range, right? You should look at that plot of tan and say, well, that doesn't have an inverse. That does not pass the horizontal line test, right? So we do some finagling to say, oh, we're going to restrict our domain and in turn restrict our range over there to sort of make that work. Okay, that leaves one left, secant and this sort of alternating upsy downsy thing. So secant, that's 1 over cosine, right? The secant of x is 1 over the cosine of x. And so let's see, we notice some nice commonalities with this cosine graph, right? It goes through the point 1, 1, flip that over, still go through the point 1, 1. But then around that sort of peak here, our function values are getting smaller, and so the reciprocal of those, we have function values getting bigger. Whee! So that's that feels like confirmation, right? That's where the secant should go. I would not like to take a test right now on that. No, thank you. Okay, let's match some more things. Now things are getting super strange. Okay, this seems like an outlier to me. That's a pointy graph. And then over here I have sort of a parabola graph and another parabola graph. I have a straight line graph. I have a swoop that's sort of increasing everywhere but goes through the origin. I have this strange thing with a big vertical asymptote, and I have this little half a sideways parabola graph. All right, let's see what we can do. I want to start with the one that looks linear, right? This looks like a line through the origin. It seems to just hit on each square, right? Over one box, up one box, over one box, up one box. That's the line y equals x. Feel good about that. Now, over here, next to it, in this first quadrant, these two graphs actually look identical, right? That looks like the line y equals x. But on the other side, it looks like the line y equals negative x, right? It's decreasing, but it's the same change. Over 1, up 1, over 1, up 1. That's the absolute value function, right? If we plug in 1, we get 1 as an output. If we plug in negative 1, we also get positive 1 as an output. Okay, let's see what we can do about these parabolas. So parabolas, looks like we're going to pick between x squared and x to the fourth, right? It's not quite an absolute value function, but it has that same sort of symmetry, right, across the y-axis. These are all even functions, by which I mean if you plug in 2 or negative 2, you get the same output. Plug in 5, negative 5, same output. Now the big difference here, this one is rounder at the bottom and not quite as steeply increasing, right? If I go over one box, I go up 2 boxes. Where down here, I go over one box, I go up so many boxes. I don't even know. The graph cuts off, right? That's a fast increase. So I'm going to say that fast increase goes along with x to the fourth, right? If you're not squaring numbers, but quadrupling them, squaring them and squaring them again, taking them to the fourth, right? Things get real big real fast. And this parabola, on the other hand, that's x squared. Let's see. Now, we've got that same relationship we saw before with inverse functions with x squared and the square root of x. That's our sideways half a parabola. That's what the function x squared looks like. You could sort of think about, okay, 1 box, 2 box, up 1 box, right? It's that same ratio, that same shape, just sideways. Let's see, y equals x cubed. Again, if we plug in bigger and bigger numbers, it's going to grow, it's going to increase. That is this squiggly over here. You might recognize, hey, that's an odd exponent, x cubed, where over here we had x squared and x to the fourth. Those were even exponents. Yes, indeed, odd exponent, it's an odd function, by which I mean it has this symmetry, but it's about the origin. It's sort of a rotational symmetry. Okay, which leaves us 1 to check. Does it make sense? Y equals 1 over x. Well, what's a number that's not in the domain of that function? A place where this function is undefined? 0, right? Popular issue to run into. Dividing by 0 is a wild time. So that's what we see here. We see this asymptote along x equals 0, along that vertical line. That is a rational function, y equals 1 over x. Okay, all right, experimental zone. I will draw for you a smiley face. And for those of you who commented that it is difficult to draw with a mouse or whatever, I concur. Whew, okay, all right, that's my walkthrough. Let me know if you've got questions. I'm eager to talk it through with anybody who's got questions. Okay, see you later.